Dr. K. Paranivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on environmental chemistry. In this talk today, we are going to see about environmental photocatalysis, one of the very important process to degrade toxic organic compounds present in the environmental samples, both in water and atmosphere. Before going to this, we will have a small information about nanomaterials. So these nanomaterials are nowadays in all type of field, all type of engineering, including environmental applications. These type of nanomaterials are finding place. So we will see what is this nanomaterials before going to look at what is the other type of nanomaterial in detail. That is material with morphological features on the nano scale, that is smaller than about 1/10 of a micrometer in at least one dimension. It should be nano dimension, and these nanomaterial may be natural material, may be incidental or manufactured material containing particles in an unbound state, or as an aggregate also possible, or as an agglomerate where at least for 50% or more of the particle in the number size distribution of one or more external dimension in the range 1 nanometer to 100 nanometer. This is a main thing. So most of the nanomaterial, whatever synthesis are available, whether it is free or agglomerated, should have a particle size from 1 nanometer to 100 nanometer. So these type of materials are called nanomaterials, and this material may be available as a nanotubes, nanowire, nanocrystal, nanoporous solid, etc. So these are nowadays in the field, in all type of engineering field or applications, everything is nanomaterial. What earlier we used bulk material, these materials are proved to show a better performance. That is why the nanotechnology are nowadays on this top. Using this nanotechnology, we will see one such type of nanomaterial in this lecture, namely titanium dioxide, which is a wonderful semiconductor photocatalysis material. Especially in nano dimension, it destroys all type of persistent organic compounds present in the environment whenever it has contact. This particular aspects is normally known as photocatalysis. That is, photolysis, already we have discussed about it. That is acceleration of the rate of photoreaction in presence of photocatalysis. Photolysis we have seen by absorption of light, and this is reaction rate is accelerated with a catalyst material, then this is called photocatalysis. So the aim of this semiconductor photocatalysis material, for example as a titanium dioxide, is to effectively detoxify the toxic organic pollutants present in the environmental samples, like pesticide, polyaromatic hydrocarbons. Everything can be destroyed using this titanium dioxide in the nano dimension. In this reaction, a photon is used to create an electron hole pairs with a semiconductor, and this leads to formation of radical species, that is with the unpaired electron, for example hydroxyl radical. This is elaborately we discussed in atmospheric chemistry and subsequently also in aquatic chemistry. This radical species, that is hydroxyl radical species, is generated, which reacts with the organic pollutant and destroying it completely into carbon dioxide and water. So such type of reactions are normally known as advanced oxidation process. Any organic compound on oxidation, if it is converted to carbon dioxide and water, this is usually we call it as a advanced oxidation process. and semiconductor photocatalysis with the titanium dioxide is also one of the very well established in this range. And not only titanium dioxide, there are many other compounds are used as a photocatalyst material. For example, zinc oxide, zinc sulfide, iron oxide, even cadmium sulfide, tungsten oxide, this type of strontium titanium mixed oxide also used as a photocatalyst material and tried. And if you look at these materials, zinc and iron etc., unstable and also corrode or subject to poisonous. For example, zinc sulfide on exposure to light become corroded, maybe sometimes oxidized to zinc sulfate. The other materials, these type of tungsten oxide and mixed metal titanium oxide are expensive as well as very difficult to produce, whereas titanium dioxide with a band gap of about 3.2 electron volt is very easy to prepare, and we will see some of these aspects of this titanium dioxide. Why it is popularly used among all the photocatalyst material, titanium dioxide is the best one and finds a lot of application, because the material is chemically and biologically inert. No bacterial thing, nothing will happen to this titanium dioxide. Inexpensive, it can be recovered and reused again in the same application, and the redox potential lies within the band gap of valence band and conduction band, so that we can use sunlight also. And how it works, this diagram clearly titanium dioxide. Suppose if it is exposed to light with a less than about 380 UV light, and this is a valence band and this is top one is a conduction band, and by exposing to this light, what happens is the valence bond generate H plus ion. At the same time, in the covalent band there will be an electron will be generated, and because of this what happens is water is getting oxidized to hydroxyl radical. Okay. H2O on reaction with this is converted into hydroxyl radical, that is an unpaired electron will be generated, and this reacts at the hydroxyl radical reacts with the pollutant and ultimately converting to carbon dioxide in water. And at the same time, in the conduction band oxygen is there, that will be converted to this O2 minus. So, by exposing to photocatalyst material, we are generating a whole electron, and this hydroxyl radical is generated, and the equations are shown here. By creating this, there should be a charge separation, the negative charge and positive charge should be separated, otherwise if it is recombined it may not lead to the formation of hydroxyl radical. So, the oxygen combines with the electron generated in the conduction band, O2 minus is generated, whereas in this H plus is generated in the valence band and reacts with water, generate hydroxyl radical as per this, and O2 can react with this H plus and generate a hydroperoxyl radical. This hydroperoxyl radical can combine with the H plus, generate hydrogen peroxide as per this equation, and hydrogen peroxide will undergo direct photolysis, generate hydroxyl radical. Here it is a direct generation from this exposure to the semiconductor photocatalysis, and the subsequent reaction also enhances, generate hydrogen peroxide, and it will undergo direct photolysis and forms hydroxyl radical. So, that reaction is much more enhanced. So, that is what the reaction, how it takes place, as I told you before, takes place. And there are some limitations with this titanium dioxide. It can absorb mainly UV light only with a less than 380 nanometer light, UV light, and UV radiation represents only about 4% of the incoming solar radiation. So, we cannot use the solar light for direct application, and because if you go for artificial UV light, it becomes expensive. We have to pay energy to glow this UV light, and this becomes additional cost for the energy what is required to burn this UV light. So, these are the limitations. Okay. So, UV light is required to activate the photocatalyst. So, how to overcome this? And if you look at the band gap between this valence band and conduction band is about 3.2 electron volts of the titanium dioxide, and because as I told you, UV light is only 4%, only about 5% it is available, and we cannot use it for very efficient way. Okay. So, what we have to do is this band gap should be reduced, so that even solar light can be utilized directly, and we have to reduce the band gap between the valence band and conduction band, so that it becomes less than 3.2 electron volts. And what are the ways to reduce the band gap is, one is the new molecular orbitals may form as a result of doping. So, doping we can go for. Doping of impurities with the titanium dioxide may reduce the band gap, so that UV light, instead of UV light we can use direct sunlight, and effectively narrowing the band gap of doping and lowering the absorption edge into the visible light range, it is possible. So, doping is a one way of reducing the band gap. And also the other ways are reduce the particle size. The titanium dioxide, whatever we are going to use for this photocatalyst material, if you reduce the particle size, I will explain this with a diagram so that you can understand better. And as I mentioned, doping is possible with both metals and non-metals, and are all proved to be effective in lowering the band gap, so that the doped cation or anion material with the carbon, sulfur, nitrogen, including fluoride is also nowadays reported. The other metals like palladium, platinum, cobalt, etc., also and doing the job in bringing the band gap. And if you look at the size of the particle employed in this application, this is a diagram with the particle size range. This is a band gap, energy band gap. You can see here at this particular range where it is minimum is about 3.2. This is, so if you reduce the particle size between about 5 to 8 nanometer, this range, if you generate or synthesis titanium dioxide particle in this range, which reduces the band gap, so that this nano sized material can be used for direct solar light. So, for synthesis of titanium dioxide, what are the precursor materials available? We can use even titanium metal, pure metal, on anodic oxidation. If you use it as an anode, titanium will undergo oxidation and forms titanium dioxide material. This is one way. Instead, we have other precursor material of both inorganic and organic compounds of titanium. Titanium chloride, tetrachloride, titanium sulfate can be used both inorganic. On the other hand, organic bound titanium dioxide also available, that is titanium butoxide or titanium isopropoxide also can be used for synthesis of titanium dioxide. And if you look at the various ways of preparing method, there are different ways we can make nano dimension titanium dioxide, the various ways, and these are all not only for titanium dioxide, these are the various ways how we can get nano material for various intended application. One of the popular method is sol gel synthesis of the particular material. Even we can go for hydrothermal synthesis, that is with the water, thermal application of heat, we can make this above precursor material to undergo hydrolysis, and then heating we can get titanium dioxide. Solvothermal, even with, because we have seen titanium isopropoxide materials are used, even organic solvents can be used for degradation and then used for thermal heating for degradation with a organic solvent, that also it will yield titanium dioxide nano dimension usually. And chemical vapor deposition, spray pyrolysis deposition, electrochemical synthesis are also utilized, and sonochemical. So, these type of sol gel etc. can be combined with the ultrasonation sound. So, ultra sound also could be used for the synthesis of this nanomaterial. Of course, the popular one is sol gel synthesis. And titanium dioxide with the appropriate precursor, whether titanium organically bound or inorganically bound to like a chloride or sulfate, what we have to do is we have to get a colloidal suspension of the sol of this one, and which is formed from the hydrolysis of the precursor material, and then polymerization reaction also will take place, both hydrolysis and polymerization by the sol gel method. You take the appropriate one, add water, it will induce hydrolysis, and also polymerization will take place, that is with which are usually inorganic metal salt or metal organic compounds such as metal alkoxide, butoxide, propoxide of titanium is usually taken, known amount of water, and it is colloidal suspension, stirred well to get a colloidal thing. So, complete polymerization, what happens is here during this process, these type of inorganic titaniums undergoes easy hydrolysis reaction, forms titanium tetrahydroxide, which on dehydration will leave titanium. Water molecule is heated to leave this one. On dehydration we will get titanium hydroxide. So, complete polymerization and loss of solvents leads to the transition of the liquid salt into a solid gel phase. Okay. The salt gel route allows the formation of highly pure substances with a homogeneous distribution of the components to the atomic scale, that is nano dimension of titanium dioxide we can get it. And this is a method usually available. Ultrasonication assisted also we can use, coupled with the salt gel process. The titanium precursor material taken in an isopropanol medium along with the water to induce hydrolysis, and which contains organic carbon source also, which carbon can be incorporated into this material as a doping also it can. So, on this hydrolysis usually under appropriate condition, what happens is the titanium hydroxide will be formed from the precursor material initially. For example, this isopropoxide material yield this material on hydrolysis, which is salt gel, and sonegation helps to bring the particle in the nano dimension of this, and on further heating this material will lose water and forms nano scale titanium dioxide, which is a very good material for semiconductor photocatalysis application. And this diagram shows you some images of a nanotube titanium dioxide prepared by direct metal anodization, titanium metal direct made to undergo anodization, which leads to formation of titanium dioxide. Okay. So, this shows the titanium dioxide formed in the nano dimension, and this is a TEM image of again nanotube of titanium dioxide formed, obtained by heating with the sonegated products of the precursor material, followed by drying at 110 degree. It generate the titanium dioxide nano dimension. The TEM image clearly shows the particles formed are in the nano dimension, and this is again doping done with silver ion. When the preparation doping is also done with the titanium dioxide with the silver, that you can see this silver incorporated titanium dioxide, that is also, and the particles formed are about 75 nanometer. That is a dimension. So, this way this is a wonderful material with the titanium dioxide containing silver as impurity, which shows tremendous photocatalytic activity for abnormal applications. So, coming to this abnormal application, if you look at it, in fact the semiconductor photocatalysis reaction was started with generating hydrogen from water. Water was made to undergo hydrolysis using this titanium dioxide to get hydrogen that is suitable for energy application. That is the main focus. It was started, but now lot of abnormal applications using this semiconductor photocatalysis. Almost all type of persistent organic compounds have proved to undergo degradation both in water as well as in air with this titanium dioxide. For example, pesticide, various type of synthetic dyes, polyaromatic hydrocarbon, everything made to undergo easy degradation with the help of this titanium dioxide, and many cases with especially titanium dioxide in the nano dimension or with doped titanium dioxide, these compounds are completely eliminated into carbon dioxide and water. So, this is a main application of this titanium dioxide, both for generating hydrogen and degrading especially persistent organic compounds, where conventional biological treatment may not work. This method of titanium dioxide comes as a very handy for abnormal applications. So far we have discussed about the synthesis and the size of the titanium dioxide particle. Titanium dioxide, as evidence from the formation of hydroxyl radical, which can bring out variety of reactions which are all very harmful to environment. Toxic organic compounds can be destroyed. Okay. And if you look at the environmental application of titanium dioxide, it was in fact it was started with titanium dioxide for hydrogen production in water. Water was made to undergo electrolysis reaction using this titanium dioxide, and they have found hydrogen was generated due to the redox reactions. And hydrogen, one of the wonderful energy material. Now it is going to be the future fuel, because all these fossil fuels is going to exhaust soon. Not only this, these fuels generate huge amount of carbon dioxide. So this way, suppose the titanium dioxide is going to generate hydrogen, which is going to be the future fuel for making energy, because the product is going to be water. If you burn hydrogen, the products are water. Water will be recycled again in the atmosphere, condensed, it will come again in the form of rain. So it is not going to be a major problem due to this water, but carbon dioxide is a major culprit. Controlling is very, very difficult. So future, now the current generation from water using hydrogen, titanium dioxide or other photocatalyst material, it is very, very slow. The amount of hydrogen generated is very low. So future, we have to focus attention using this titanium dioxide or other photocatalyst material, or the modified photocatalyst material, which can work with the solar light and generate more amount of hydrogen. That is going to be the future energy technology. So that way, this titanium dioxide and other photocatalyst material is also going to take part in energy technology applications. So coming to the main application of environmental degradation, one of the main thing is we have plenty of toxic synthetic organic compounds as well as endocrine disturbing compounds, which are all considered to be the emerging contaminants, which is persistent in environment for longer time, difficult to degrade by conventional biological method, is creating a lot of worry for environmental person because of the toxic issues and health related issues. Everything is arising because of this persistent pesticide compound, different type of synthetic dyes, polyaromatic hydrocarbons, biphenyl compounds, and various chlorinated compounds are a huge worry for environmentalists. And using titanium dioxide, we can destroy all these toxic organic compounds, pesticide, dyes, polyaromatic, everything with the help of titanium dioxide, especially nano dimension titanium dioxide or the doped one, we can completely degrade them into carbon dioxide and water, or the any chlorine is there, that is also eliminated. So this way, this titanium dioxide is going to be the future technology of advanced oxidation process, in which we can combine solar energy so that the cost will be considerably reduced. No UV light, because burning UV light requires energy, and we are going for direct sunlight capture of this one to minimize the band gap below 3.2 electron volt. Definitely this is going to be the future technology, especially for degrading this POPs, that is persistent organic pollutants, which are all very difficult to degrade in the environment. Titanium dioxide is one of the nanomaterial, wonderful nanomaterial for environmental applications, and we have discussed how hydroxyl radical is generated by exposing light, UV or solar. This converts into hydroxyl radical. The hydroxyl radical, already we have seen, is a very powerful oxidizing agent. It will destroy all type of organic compounds. Okay. Only thing is, during this formation of hydroxyl radical, we have to see that the charge separation, the whole electron negative and H plus should not be allowed to join. So that will prevent the generation of hydroxyl radical. If charge separation is taking place, then titanium dioxide can generate continuously hydroxyl radical by exposing to light, and that is sufficient to destroy all type of organic compounds. Coming to the preparation of this nanomaterial, again very easy, simple salt gel method coupled with the sonegation, we can generate nano dimensioned titanium dioxide particle. And titanium dioxide and if you are getting particle size less than 10 nanometer, which is a very good one for solar light direct application, because particles in that dimension is capable of absorbing solar light directly, similar to anions on cation doped titanium dioxide also. So, this material is already proved in the environmental field, both for environmental application to destroy the persistent organic compounds and toxic organic compounds present in the environment, both in water, wastewater as well as air. It can do the job. Similarly, in future energy generation also, this type of material is going to replace the fossil fuel with a environmentally benign hydrogen. So, thank you very much. With this, we complete this lecture on semiconductor photocatalysis. Thank you once again.